So I will not say anything about Nottingham. I'll just go straight to my presentation, which is the description of a European project that we did and ended up 2-3 years ago, but they were still working on it. And then regards power electronics for universal and flexible power management in new power networks. So the idea was to produce a converter which could be used as an active node into a power network in order to manage power coming from different sources and connect it to the network itself. So the idea was to have a sort of electronic transformer, but at the same time to have an active node, a sort of energy router, which would be able to possibly manage power from different parts of the network to other parts of the network. So for example, imagine here we have the idea was to have a 3-port converter. However, since the converter has been built as a modular converter, you could imagine to have even more ports rather than 3. The basic concept was to have 3 ports, in which, for example, look at this, you can have a wind energy power source on one side, energy storage on the other side, and a connection to the network on this side. In the view of what is called smart grid, active nodes like these are very important because they can receive information and control from a supervisory control system in a way to manage and route energy in the way that it is required by the director of the power network. So it can be used for interfaces renewable energy, but it can be used to interface also traditional source of energies or simply for power management. So for deciding how much power goes from one side to the other, and also, we will see later on, also to operate some operation on the power itself. So that is the concept of the UNIFLEX. So I'll try to concentrate in half an hour on what was this project, even if we are still working on it, and I will see it later. So the idea of the converter was a 3-port converter capable, as I said, of connecting 2 different networks, for example, and a 3rd port connecting, for example, energy storage or a low voltage network systems. It is made by a modular cascaded 8-bridge multi-level power converter with bidirectional power flow that is directly connected to the grid. Now, as I said, this converter can not only perform power management and flexible power management, but can also perform, for example, voltage range adjustments. So, for example, if voltage at port 1 changes, voltage at port 2 and 3 still stays in their nominal value. Or frequency changing, so frequency at each port can be different. Okay. Phase changing, asymmetrical load current cancellation, voltage asymmetry cancellation, reactive power control, and now even active power control and active filtering capabilities. So this converter can, whatever is the situation given in one port, I manage that at the other 2 ports we have nominal conditions as we require. This is the configuration of the converter that we have built in the end. So we have cascaded multi-level H-bridge converters. So as you see, port 1 is characterized by 4 H-bridge in series for each phases. So we're talking about a 9-level multi-level converter. 3 of these H-bridges are connected. We will see, I will explain later on what is the modular element in here. But 3 of these H-bridges are connected in order to form port 2, which is the second high power, high voltage port. It will be 3 H-bridges converter here in series, which will provide a 7-level multi-level converter on this side. And only 1 for each phase of this H-bridge are connected to the low power port in order to form a connection with the 3rd, for example, storage elements or even low voltage systems. So as you see, port 1 is the port on which we have to perform the general power control, because this is the only one port which is connected to both the other ports. The structure allows the converter to be arranged in parallel series combination to meet all the power level. You can see that each of these parts here, so H bridge on one side, H bridge on the other side, and a DC to DC converter in the middle with high frequency transformer isolation, is what we call the building block of this converter. And you can imagine that according to the power that your system needs to have, you can connect many of those things in series in order to meet the power requirements. So this is the building block that we are talking about. So we have an AC system on one side, an H bridge, and then here a dual active bridge in the DC to DC converter where we have a high frequency transformer in the middle. Well, we say mid frequency transformer because in the end we've used a frequency of 2 kilohertz for that transformer. So, and that provides isolations between the three ports. And this is the building block. On the other side, after the DC to DC conversion, another H bridge which reconverts the power to AC. Since the target application is for high power, switching frequency must be minimized in order to keep down the losses. Okay? So in this case, we are using the switching frequency of each AC side H bridge up to 250 Hertz. So it's a very low switching frequency in order to operate the system at very high power. This system could be, the idea of this system could be applied also for very high power. We were foreseeing at that stage even applying for 5, 10 megawatts. Of course, the prototype that we built in the lab was not at that level, but still was a 500 kilowatt prototype. So for a university facilities, having a 500 kilowatt system like that is quite a substantial thing to do. The phase shift carrier PWM modulation was in the end chosen as modulation for this system, so for the cascaded H bridge multi-level converter on each port. Now let's talk about the isolation module, which is this DC to DC converter here. That is the structure, still made all H bridge, so all the thing is very modular. You can just remove one bit and then plug and play and make it as big as you want, depending on the application and the power application you're doing. So we are talking about isolated dual bridge DC to DC converter, which have bidirectional power flow and soft switching ability thanks to some snubber that we put on the component. We have a simple control which manages to have the DC voltage at each side of the converter exactly equal. Okay? So the error between this E2 and E1 is driven to 0. And the way in which it is done is simply by playing with the phase shifts of these two, of the square wave produced by the two H bridges, playing with the phase shift, and of course, knowing the inductance of the transformer in the middle, we can make sure that we drive the DC voltage on the two sides to have the same value. We have used a 2 kilohertz mid-frequency transformer here in order to perform the isolation between the modules. So that was the description of the converter. Let's go now to the control challenges of these things. The fact that we managed to have, the equivalence of these two DC voltage on each side of the DC to DC converters makes sure that if we assume that, and if we assume that control works, the two things need to be taken into account for the control of this converter. First of all, the global power flow control. So the power entering through one port must leave from the other two. So that's a global power flow control that needs to be implemented in the converter. And the internal power flow control. So the energy must be distributed amongst all the cells in such a way that the DC-link capacitor voltage remains equal. Okay, so we have a multi-level cascaded H-bridge converter. The DC-link voltage on each of these H-bridge needs to be kept constant in order to evenly distribute voltage stress and also to ensure high-quality voltage waveform at the AC connections. So in our configurations, port 2 and 3 control the power for the grid storage system that which are connected to, and port 1 is the global power flow controller, since it is the only port which is connected to the other two. The first control that we have implemented for this system is a classical DQ control system, where we have a lot of nested control loops and needs very careful design. Of course, the more the more of these building blocks we have, the higher is the power, the more are the DC link voltage we need to take into account and we need to control and we need to balance. So we can see here, we have a voltage control. The global voltage control ensures that the total DC link voltage on each of this side of the converter is as demanded. So this ensures that the global power required for the converter is drawn from the grid at port 1, for example. Then we have a current control. A current control which is applied in DQ reference frame. This actually is the first implementation we've done. Of course, then we have tried different kind of controls, so we'll just talk later on about one of those, because we need actually a per phase control of this system if we want to be able to manage with unbalanced systems and with many other different issues. So at the moment, I'll describe this DQ control in a stationary reference frame. And also, in this point 3, we also require a system that balances all the DC link voltages on each of the H bridges. So these are the three main parts of this control. So general voltage control, which is also power control. The current control, which is done in DQ in this case. And then the balancing mechanism for managing to have the DC link voltage on each H bridge staying equal. Let's briefly talk about the converter prototype, just a few information. So the converter was designed for operation at 3.3 kilowatt, which is mid voltage in the UK, with a power rating up to 300 to 500 kilowatt. This is what is the prototype that we have built in the lab. Obviously, the same system can be applied for higher power. Each UNIFLEX module is rated one of those building blocks. Each of them is rated about 25 kilowatt with a DC link voltage of approximately 1.1 kilovolt. The two H bridges and the DC link are connected to each side of the transformer. We're talking about a 3.3 millifarad DC link capacitor at 1,350 volt. The modules are 1,700 volt, 200 amp modules Dynex with forced air cooling, and the gate drives are isolated for several kilowatt. The control of the entire converter is implemented by using the Texas Instrument DSP, the 6713, with 5 FPGA boards. Okay, the 5 FPGA boards are due to implement modulation and other control systems on each part of the converter, but the general control is performed by this DSP of the Texas Instrument. The DC-to-DC converter, the isolation modules I described earlier, are controlled only using FPGA cards, while the global power flow control is implemented on the DSP. The ABB actually designed, ABB was part of this European project, and they designed the mid-frequency transformer for operation at 2 kHz. Let's see if I have a figure now. Yes, so this is the total image of the converter, where you can see the H bridge at each side of the transformer. So the H bridges plus the DC-to-DC converters, including the mid-frequency transformer in the middle. Now, These transformers here could have been done much smaller than they are. It was because ABB wanted to use the same case that they already had. So they could actually be made 3 times smaller than that. So that would reduce the size of the converter substantially. And in the end, we went on with this configuration. We can see each module, the transducer's box on the top of here, the IGBT gate drives and the components, and the DC-link capacitors down there. So that was the final hardware setup, which is still in the laboratory of the University of Nottingham, still being used because we are doing a lot of more tests on this system. No? This is just an image of the DSP with the 5 FPGA cards and all the fiber optics and system of the control part of the converter. Now, let's go to some results of this. So far, we have tested this converter. By the end of the European project, we have tested this converter only in a 2-port configuration. We are now actually testing it on a 3-port configuration. So what we have here, in the 2-port configurations, both on port 1 and port 2, we are using 3 H bridges in series in order to have 7 levels on both sides of the converter, still with the isolation modules working there. Power flow can, of course, go in both directions. And port 1 and port 2 are connected to two grids. Operated, we have most of our tests are, of course, made at 415 volt normal low voltage in the UK. But we have also done some tests which I'll show at 3.3 kilovolt. And we have shown a potential of bidirectional power flow up to 300 kilowatt. These are the characteristics of the converter. You can see some values of input supply inductance, input filter inductance, rated current of the H bridges, rated voltage. So with actually, at the moment, a sampling frequency for the control use of 3.6 kilohertz. So these are some experimental tests for real power flow in both directions. So you can see figures of port 1 and port 2, and according to the phase shifts between the current and voltages, you can see, in this case, power flow from port 1 to port 2. This is the waveforms at port 1, and these are the waveforms at port 2. So the red is the supply current. The green, as you can see, is the 7-level multi-level voltage, and the supply voltage is the blue figure. On this side, we can see the power flow from port 2 to port 1. As you can see, the current at port 2 is in phase shifts of 90 degrees compared to the voltage, while on port 2 they are in phase. So now, as I said, the switching frequency of each of the devices in the converter was 250 Hertz in order to maintain a low switching frequency, since this converter needs to be used for very high power. This shows how the DC-link capacitor voltage control works. So we managed to, these are the 9 capacitors, as you can see, since we have 3 H bridges for each phase. So in this case, you can see that reference and real voltage are, the real voltage tracks the reference. When we have a step change just before 2 seconds here, we can see that the voltage control and the voltage control on each H bridges works properly. This shows the 4-quadrant control on port 2. So you can see in port 2 negative active power and here plus and minus, positive and negative reactive power flow. Still in port 2 here, positive active power and then positive and negative reactive power. You can see on the basis of the phase shift of the quantities shown here. You can see that the current, of course, is multiplied by 10 in order to have a decent waveform to show together with the voltage. This shows the power flow control, the cell power flow control for unbalanced cases. So when we have, starting with DC link voltage difference from each of the three, on each of the 3 H bridges, and we activate the balancing control algorithm, you can see that immediately, or in a very short time, the balancing algorithm works, and we can have a behavior using a correct balancing scheme where all the DC link voltage are kept constant. This shows the possibility of using the converter for connecting two asynchronous systems. So if port 1 works at 50 Hertz and port 2 works at 60 Hertz, we can see that we can manage the power flow regardless. So port 1 goes at 60 Hertz, while port 2 goes at 50 Hertz. And we can still manage the power flow on two asynchronous networks. And this shows the medium voltage testing. So you can see that the voltage here is 3.3 kilovolt. And then it shows switching frequency approximately 250 Hertz. And these figures are more or less for a 205 kilowatt power flow. So you can see power flow from port 1 to port 2, power flow from port 2 to port 1. And these are the port 1 waveforms, and these are the port 2 waveforms, similar to what we've seen earlier. The red is the current, blue is the voltage, and the green is the PWM voltage. So you can see how the system has been tested and validated also for high power flow in our labs. Again, this shows the 4-quadrant power flow at 3.3 kilovolt, where we have in this case, these are 4-quadrant controlling port 2 at 3.3 kilovolt. As you can see here, the power was 285 kilovolt ampere. So we have here both negative active and reactive power, here negative active power and positive reactive power, here positive active power and negative reactive power, and here positive active and reactive power. Okay, now this was done with the control, with the DQ control on DQ reference frame, which does not really take into account per phase problems like unbalance that can be dealt with in a per phase configuration. So some advanced control strategy to control the converter per phase basis were needed. This was needed to monitor each phase of the supply and track the grid angle of each phase independently. So the PLL should be able to track the grid angle of each phase independently in order to guarantee a proper control on each phase. Also control the power flow on each phase independently and operate under condition of grid disturbance such as phase jumps, voltage sags and swell, fault condition and frequency excursions. So we need to test the converter on these things. Of course, as I underlined earlier, low switching device frequency modulation is required to minimize the switching losses for operation at high power. We have tested a lot of different control per phase, dead bit control, but what I'm going to show here very quickly is, since Professor Olds had talked about model predictive control, we have applied the model predictive control on this system. Obviously, Professor Olds has already described what model predictive control is, so I'm not going to go in detail, even if this implementation is a finite state model predictive control, so a little bit different from what Professor Olds explained, but the concepts are basically the same. I'm not going to go through this. But the idea is to, like you were asking actually earlier, if we could combine the control of the voltage on each DC link or a multi-level converter with the model predictive control. I think some of you was asking this. Yeah, we've done this here. So you can see that this is only port 1. Okay, I'll just describe on port 1. We have 3 H bridges per phase. Voltage was was included also into the predictive control algorithm. Here there's a PLL, so we implemented a model predictive control for these things, also not only controlling the current, but also active and reactive power. Okay. We're going to go through this. It's all based on a per-phase modeling of this input side of the converter to control the current of this input side. So I'm not going to go through details on this. And this was basically the structure of the block scheme. Again, I'll go very quickly on this. There is an active and reactive power. If you see the prediction of power, so we have the prediction of active power, reactive power, the control of the current using predictive control, and in this particular application, in this particular case, we kept the voltage control on each of the H bridges with PI controllers in order to guarantee the balance between the different DC link voltages. So even with model predictive control, we have converters away from port 1. As you can see, the converter works well in this case. This is wrong, sorry. The sampling frequency was kept at 3.6 kilohertz. I don't know why I said 10 kilohertz there. The sampling frequency, not the switching frequency. The switching frequency, even with predictive control, is very low. We're talking about the order of 300 hertz for each device. Okay. This shows how we can perform real power flow control from port 2 to port 1. As you can see, the power flow control is done very well. This is the reactive power flow from port 2 to port 1, setting different reference value we can track, and we can decide how much power is reactive power or active power is transmitted. And here, being a per-phase control, we can perform a lot of different operations, like, for example, seeing what happens for grid voltage excursions. So, of course, we are talking about very worst-case scenarios where the voltages changes all the time. So here we have voltages, input voltage will change a lot of times. We're talking about PU operation here. Active power is changed at this point, active power reference is changed at this point, and still the system performs quite nicely, while the reactive power is kept at 0. DC link voltage also is kept more or less constant, with some variation due to the voltage excursion in the input side. Here for grid voltage imbalances, same story. DC link voltage is kept constant, reactive power is kept controlled at 0 in this case. Reference active power is tracked. Here also in the case of grid voltage imbalances. Harmonic content of the converter, we have, giving the switching frequency very low, we still managed to get a 3.37% of THD on the input current, which is quite a good achievement. Finally, just briefly, one-phase short circuit. As you can see here, the converter reacts very well both in active, reactive power and DC link voltages. Two-phase with ground short circuits. Again, the converter reacts decently well for these cases too. That was the summary, very, very brief summary of what this project was about. It was to demonstrate that it was possible to build an active node, high-power active node capable of routing energy into a complex grid. Okay. Next, what we are doing next is to use the third port, is to make sure that power is shared and power flows into the 3 ports, which we didn't manage to do by the end of the European project. That's what we are doing right now, and possibly next year I will be able to show you some results for the 3-port system. Okay, so I think that is for me now, and I'm finished.